By the way, so does anybody want to make any Skype calls? I found the number for it, so anyone we can just do them now. We can just spend 45 minutes on Skype calls. So today will be the third and fourth lectures on deep learning theory. And as I mentioned, it's a big topic. We could have, just done machine learning summer school on deep learning and deep learning theory if we wanted to. I just chose some topics for yesterday, some topics for today. And as I warned you, today will be much more biased. Today is going to cover much more recent work, and I guess maybe necessarily my expertise in this more recent work is much lesser. The stuff we talked about yesterday, I've been reading about it since I was in my first year of undergrad, and this stuff, a lot of the citations from today are from 2019. So, okay, so just to recap a little bit, so thanks for having me here. We all remember who this guy was. And why didn't somebody tell me what we did talk about yesterday? What did we talk about yesterday? Anyone want to? Uniform approximation. I don't know what that means. What is that? Universal, what is that? Tell everybody what that is. So we can approximate continuous functions with deep networks. And was it practical? We had exponential width for a lot of constructions, and a lot of the deep constructions were very special cased, and so it's unclear how practical some of this was, but it does have a lot of nice insight. So that was yesterday, and today what we're going to cover is optimization and generalization. Now this is where my bias is going to come in, and I'm just being very explicit about this. So for optimization and generalization, I have a specific perspective that I like, that I believe in, that I work on myself, and it's the main way I currently and some other people see how to maybe make this story all make sense together, and that's using something called margin theory. So there are many ways we could talk about optimization and generalization. The problem, of course, is completely wide open still, but I'll use this margin perspective. Okay? All right, so here's the basic outline. And actually, it'll be more like 4 parts because of lunch. So first, I'll tell everybody what margin theory is, and that will be a non-deep learning part of the talk. So that'll be margins. I'll go over the classical theory. Just checking. So that'll be margins. Then I'll start talking about deep learning. I'll talk about actually 2 things. One, I'll talk about the fact that empirically, it appears that this margin phenomenon is happening in deep learning. So I'll just empirically verify it. I'll run some code, I'll make some plots, and maybe argue to some extent that it does seem to be happening in practice. And then I'll provide a generalization bound based on that. And the way I think it's going to go is we're probably going to start after lunch with the generalization bound. Okay, and then the last thing is we'll talk about optimization. So the way this margin theory works is, margin theory says that if you have predictors, if you have functions, if you have deep networks with certain nice properties, then these generalize. So then we actually have to do 2 things. We have to prove that these things generalize, and we also have to prove that the standard algorithms we use actually produce these things. People just run gradient descent on cross entropy. It doesn't say find these functions with these good properties. So we have to do both, and that's the goal in the optimization part. And the second 2 parts of this talk are very incomplete. They will not answer the question. I'm not throwing any shocking new results out today. Okay, is everybody fine with what we're doing? Okay, so yeah, my bias is revealed. All right. So let me first tell you about margins. So this is a very classical theory. It's existed actually since the 60s. At least. I mean, it's just one reference I know of happens to be from the 60s. And it's a standard way to analyze generalization and optimization. And as I'll argue, it seems to have certain attributes that make it well suited to apply to deep learning. That said, it's not going to completely solve the problem today, but it seems to apply. And so that's why I'm doing this. I should note that I will point out other ways to reason about generalization and optimization in deep networks. And at any time, if you have a question, oh, I read some paper, I saw some paper on arXiv, I saw some paper on Twitter, right? Nobody goes to conferences anymore, they just read Twitter. This is 2019, right? So if anybody has any questions about any paper they saw somewhere, feel free to just interrupt me and ask about it. Okay? Just because I'm talking about margins doesn't mean we all have to talk about margins the whole time. And I will give some other results. Okay, so yeah, my biases, I'll keep revealing my biases. I should say, I mean, there are other research groups working on this approach, but it's not everybody. Okay. So let me give you a backstory. So back in 2017, I personally, very early 2017, like January 2017, I had been working on a lot of these approximation results that you saw. I had just proved this depth separation result that I presented last time, and I was very much in the approximation theoretic setting. And then this happened, okay? This paper happened. How many of you have seen this paper? Okay, so this paper, I'll explain a little bit about what it says, but this paper shocked a lot of people, and this is actually a really cool paper because even though some people like it, some people don't like it, it seems everybody fights about it. Everybody that knows about it fights about it, so it got a lot of people really motivated. And so I was in Berkeley at the time, and I was just sitting front row. Ben Recht came, gave a talk, and I was just sitting in the front row, and I was just angry the whole time. And I went upstairs, and I checked everything he said on a computer. So this paper motivated me to do lots of nice programming, and it got me out of my comfort zone. So it's literally this paper and the talk by Ben Recht that got me to kind of stop, to some extent, working on the approximation theoretic stuff I was doing yesterday. Okay, so this paper really highly motivated me. So this is a cool paper for that reason. Okay, so what does this paper say? So this paper, what it does is it runs a bunch of very nice experiments on Google hardware, so the experiments are, pretty plausible. You can't just like kick the experiments in the trash by saying they didn't try enough hyperparameters or something. They're pretty plausible experiments that say that many core kind of rules of thumb, or according to them, many rules of thumb of statistics kind of don't apply to deep learning. We have to do a different approach to generalization. For me, there were actually just two things that really shocked me when I opened this paper. So one was that they always get zero training error. Okay, so I actually thought something was weird about the experiments or something. I had not, at that point, never used TensorFlow myself, or any of these big, I just did small scale deep networks that you can just code up and, just with like matrix multiplies yourself. But just out of curiosity, how many people have done these experiments? Oh, good, so I'll explain what this is. So here's an experiment you can just run. Take MNIST or CFAR, okay? Just take MNIST or CFAR and some architecture you believe in for both of them. So for CFAR, you can get zero training error very fast by using this thing called AlexNet. It's just a couple conv layers, a couple fully connected layers. So you run, you get zero training error, and then here's what you do. You randomize the output labels. Okay, you randomize the output labels, which means you're learning a random function. It's kind of a maximum complexity function. And then you refit and you still get zero training error. Okay, I actually just read the paper and I was like, surely it's because of the optimization method, something about the architecture, something about the initialization. I was like, there's no way this really, does everybody understand how weird this is? So when we were in Justin's talk, he was like, oh, gradient descent, you follow this path. This thing is super non-convex. And you add random labels, it's ridiculously non-convex. Okay, saddle points everywhere, and that's not even the smallest of your problems. Small smoothness coefficients, like everything is disaster. So I was shocked. So what I did is I went upstairs and I implemented it wrong. Okay? I looked at the spec of AlexNet and I implemented it wrong. I divided the widths by 2. I didn't use Atom, I used SGD with a stupid learning rate. I did everything wrong. And I still got zero training error. And I kept breaking the code and I kept getting zero training error. I was in this loop for a day. And so this was shocking to me. So these things really do get zero training error. To be clear on these classification problems. If you try to do an RL task, it does not get zero training error. But on these, it gets zero training error and it's shocking. And it still generalizes. Okay, so I read this paper and I was shocked. And this paper similarly shocked many people. It's influenced many people, and it's made many people very excited about doing two things. One, proving that gradient descent actually does this. So now we have two tasks. One, we have to prove that gradient descent gets zero training error, already hard. And then we have to prove that it gets zero test error, or near zero test error. Very hard. Okay? So this paper was very exciting and very motivating for a lot of people. And one thing in the abstract that just sort of grabbed me is the abstract said it's unaffected by explicit regularization. So to remind everybody, explicit regularization, the easiest form of it is we have our risk, we're minimizing our risk, and we add on, let's say, L2 norm of the weight squared. Okay, that's regularization, one version of it. So on the training set. So on the training set, so to be clear, one nearest neighbor also can get 0 training error. The shock here, but what is the, it's memorized, so one nearest neighbor can get 0 training error if the inputs are distinct, but it memorizes the data set. So this thing is like, you see what I mean? This is cool. Like, maybe one of the first things, if you're like a nearest neighbor person, you look at this, you're like, oh my God, are deep networks doing a nearest neighbor? Are they memorizing the training set? Like, what's going on here? This is pretty crazy. Yeah, I very highly value the fact that your immediate reaction to what I said was like, surely you've made a mistake in what you've said. That's how I felt the first time I heard it. Yeah, this is shocking. Yeah, of course. Right, so if you have implemented your random generator correctly, then on random labels, the error rate has to be the label proportions. I mean, it has to be, the majority vote. So, so yes, on CFAR, which has 10 labels, it's actually not exactly balanced, but you get roughly 90% error, not 90% accuracy, 90% error, which is the best possible. When I say it still generalizes in the random label case, that is the best you can do. But on the true case, it gets this ridiculously small test error. Yeah, it's totally amazing. Yeah, I'm friends with the authors, and they get lots of like feedback about this paper still, some positive, some negative. I just think this is if anybody reads this paper and they have either positive or negative feelings, the exciting thing about this paper is just motivated everybody. Okay, so yeah, check it out. All right, so one thing that kind of grabbed me when I read this was just in the abstract, it says not affected by explicit regularization. And this margin theory, let's see if the echo a little better. This margin theory that I was telling you about, it also works in the regime of no explicit regularization. So I saw this, I was like, I'm going to apply margin theory. Okay? But many people read the abstract and they ignored this sentence, or they didn't think it was important. So again, I have my bias, it's that I like this margin theory. Okay, so explicit regularization not needed, it's like that. And like I said, there are other ways that we could talk about this without margins. Okay, so what are margins? So when we've been talking about, well, I don't think anybody's explicitly written this down yet. Maybe I missed something, but whenever we have classifiers, the way we actually implement them in deep networks is, oh, by the way, so the echo isn't bothering anybody? I can switch to a hand mic. Everybody's fine. Okay, I'll stop complaining. All right, so the standard way that we get classifiers is we train up something which is a real valued predictor. So your network, it outputs a bunch of real numbers. And then in the binary case, we take the sign of the output. And in the multi-class case, we take the largest output. Okay, that's how we discretize it. But we're throwing away information when we do this discretization. It's also interesting to look at just the real numbers themselves. Okay, so in the binary case, what we can look at is fx times y. Okay, so f is my neural network. It outputs some number. And we want the sign to be correct, which means we want the sign to agree with y. So if fx times y is positive, I make the correct prediction. You can check that in your head for both y's -1 +1 cases. And it seems like it might be good if the number is very large. In the softmax case, for instance, our network has a softmax output, you interpret it as a probability. This means that there's way more probability on one output than the others. Okay, this is totally intuitive. So far, what I've said actually has a bug in the sense that I've called it an unnormalized margin. If we say that, oh, I want the margins to be bigger, then I can just take my deep network that gets 0 training error, I can multiply the output by infinity, and I'm getting plus infinity confidence and everything. So there's some notion of normalization we have to work out. So whenever we'll talk about margins in this, it'll always be the margin normalized by something. So I didn't put it on this slide, but to be clear, in the binary case, we'll have fxy divided by some number, and in the multi-class case, it'll be that difference divided by some number. Let me just explain the multi-class case. It's saying it is the value on the correct output minus the largest output on something that was not the correct value. So that number will be negative if you made the wrong prediction, and it'll be positive if you made a correct prediction, but it might be very small or very large. Okay, so some history on this. So the perceptron algorithm, provided without an analysis, but then a very nice analysis was given that said that if this margin in the linear case, for linear predictors, if this margin is some number, then the number of iterations that the perceptron algorithm needs to find a correct classifier is 1 over the margin squared. So this was amazing. This is from 1962. I want to say down the street, but I actually don't know what city he was in. So, does anybody know where Novikov was? Okay, whatever. He's not in the room, I guess. So, okay, so that was 1962. Then the SVM, of course, is based on the concept of margins, though I need to check the history carefully. I've seen reports that actually the original, it took a while to produce margin-based generalization bounds for SVM, and the first actual margin-based generalization bound was in 1996, and it was for two-layer networks, actually. So it's by Peter Bartlett, and this is the title of the paper. So check out the title of this paper. I don't know how often we get a title of a paper which is a complete sentence that could just, you could just suffice with the title, but I'm just going to read it out to you. For valid generalization, the size of the weights is more important than the size of the network. So let me explain this. So I was saying that that paper by Ben Recht and Moritz Hart and a few other people, Sami Bengio, I was saying that this paper kind of contradicts some intuitions from core statistics. And one of the intuitions is that if you increase your number of parameters, your test error goes up. Okay, there is such a rule of thumb. Some people have this rule of thumb. And what this paper is saying is that's not the right rule of thumb. The title of this paper is you don't care about the size of the network, aka just the number of parameters. You care about the size of the weights in the network. Okay. So, and then the real kind of, so I'd say there were two, I should have put more on this slide. So I would say there are two major successes of margin theory. One is that it was used as an explanation of boosting methods, and it was also, of course, pivotal in every way about SVMs as well. Okay, so okay. So let me just say a little bit about the story for boosting in a little bit more detail. Okay, so the story with boosting is like this. So standard boosting methods, you can prove they can get zero training error. If you want to be technical, I'll just say what I mean by standard boosting method. Take EdiBoost and use shallow decision trees as your base classifier. If you know what those words mean, then this answers the question. Okay, so you can prove it gets zero training error, and you can prove that the testing error is the training error, which is often 0, plus some number that scales with the margin. Okay, good? So let me just go through these bullet points because I skipped one. So the first one is saying we can guarantee get zero training error, but we can do better than that. We can actually guarantee that boosting methods find large margin predictors. Okay, they don't just get zero training error, they get zero training error with that margin, that normalized margin being a large quantity. And then we have bounds based on that normalized margin. Okay, so here are the parts of the story, and let me read the colored text now. So empirically, we have seen that we get zero training error for deep networks. On the second bullet point, I haven't said anything about whether we empirically observe large margins for deep networks. And of course, then we're left with proving that gradient descent finds large margin deep networks and proving that large margin deep networks generalize. Okay? Okay. So what we'll do in this talk is so I'll review the margin theory for boosting. I'll review the margin theory for boosting. Then I'll show you the empirical evidence that we get large margin deep networks. So that'll be this empirical point. Then I will give you a margin generalization bound. So that one proves that if you have a large margin deep network, then it has good test error. And then I will give some results about being able to optimize and find large margin deep networks. And I should say that all of this is like, super work in progress, and we're like years off from solving this problem. But I'll do what I can. Sound good? Okay. Any questions? All right. Okay, so let me just review for you the boosting literature. Yes, that's my plan before lunch. That's why I keep checking my clock. Before lunch, I want to tell you what the boosting literature does, and then I want to tell you that deep networks find large margin predictors empirically. So we'll end lunch and we'll maybe somewhat believe that it happens empirically, and then after lunch, we'll actually try to go through the theorems that why this happens. Okay, so just a reminder, because I realized that, so when I was, when like Arthur and I were like, you know, when we were like learning what is machine learning, we were told very different things than everybody in this room. You know, we were told, you know, you go and you do your SVM and your SMO and your libSVM and your SVM Lite and your AdaBoost. Yeah, the world has changed. And so this is boosting for people that have not seen it before. So boosting is a method that you have a big bag of classifiers and you want to add them together to get a much better classifier. Okay? And for people that don't know the intuition behind it, the intuition is that if all of you are like a random coin, if I ask you some question and you all have probability, you know, something slightly better than random guessing of getting it right, then if I majority vote all of your answers, I'll get something very close to a correct answer. Okay, so the algorithm, the way it works is it greedily kind of reduces its training error by just picking what feels like the best fitting function from this bag of functions it has and adding them to the current ones. I won't go through the details of the algorithm, I'll just say it's some greedy coordinate descent type thing. And the predictor it outputs is, so you have all these classifiers, you selected H1 through HT, and then you take a linear combination of them, so sum j, wj, hj of x, that's your output prediction. So I mentioned that when we talk about margins, we need to normalize them in some way. And in order to get our theorems to work for boosting, the correct, or one of the correct notion of normalization is the L1 norm of the weights. So I just take the weights, I sum up their absolute values. So again, here's the definition of the margin for the output of the boosting algorithm. I have this majority, or this majority vote output. I multiply it by the label, and I divide it by the L1 norm of the weights. Okay, that is my normalized margin on a fixed example, and then I take minimum over I, and that's the minimum margin over the training set. Okay, so now we have finally a normalized margin written down mathematically. Okay, so this is where things get interesting. So the way people train deep network, or sorry, that was a strange break of my brain there. The way people train AdaBoost is they use coordinate descent, and they use coordinate descent on things like the logistic loss, the exponential loss, cross entropy. They do not explicitly maximize this margin. They minimize some other quantity. So it's not obvious that the training problem gives you a max margin predictor. And the fact that we use this L1 norm is due to coordinate descent. Okay, so here's the generalization bound you can prove. Let's just check the time. Yeah, let's go through this so that we all understand it pretty well. Okay, so fix some bag of classifiers H with VC dimension H. If you don't know what VC dimension is, let me just tell you the key point about VC dimension. We might have infinitely many of these classifiers, but they have to be kind of well behaved. Okay, this number needs to be finite. If it's all linear predictors, it's going to be the dimension of the data. So it's things that are not too crazy. But the reason this is interesting is because this theorem allows us to add together effectively infinitely many different little base classifiers and still get generalization. So the way that you should interpret this in context of deep learning is I can have a deep network that has an infinite width or infinitely many layers, and there's still a hope of getting a good generalization bound. You can have infinitely many parameters, it can be fine. Okay? Because for every classifier, I have another coefficient wj. So I have infinitely many parameters potentially. Okay, so that's why this is maybe relevant to deep learning. Okay, so here's this theorem from Shapiro, Freund, Bartlett, and Lee. This is the same Peter Bartlett from before, and Shapiro and Freund came up with AdaBoost. So we have our bag of classifiers, and you fix some margin level. It can be the max margin if you want. Then with probability 1 minus delta over the data, for any predictor, here's what we can show. We can show that the probability of error, the probability that you have a misclassification with this predictor with weights W, is less than or equal to the empirical probability. So on the training set, the number of margin violations. So let me just explain this. Number of margin violations means that I fixed my level of margin gamma, and I have my normalized margin on the different examples for this predictor, and I'm asking what fraction of them are above that margin level. Okay, so how many margin violations I have on the training set. Plus this term that scales with the VC dimension of the bag of classifiers, and in particular not the number of parameters, divided by root n, which is standard in learning theory, and the margin gamma. So let me just drive the key point here, which is that this boosted classifier that I only wrote explicitly here, I can have infinitely many wj's, and this thing can still say small test error, because the number of wj's does not appear in this bound anywhere. I didn't drop it. Okay, so just for the context, here's that quote or that title from Peter Bartlett at the bottom: for valid generalization, the size of the weights is more important than the size of the network. That's the point here, that we depend on some other property of the predictor, not the number of parameters. Okay, so that's the bound, yeah? So the way this thing, so we just need their VC dimension to be finite. Is that answering your question, or? Weights, or? Not the weights, but the VC dimension finite. That's really it. Oh, I guess, I mean, since they're classifiers, their outputs are between -1 and +1. I don't know if that matters to you. But. Okay, so here are a couple remarks about this. So here's an interpretation of this. So actually, let's read the second line here first. So the PR hat, this empirical probability of margin violation, if we expand margin violation, it's saying that gamma that I provided you, this gamma is greater than the unnormalized margin y f of x divided by the L1 norm of w. So here's another way to think about this thing. If your predictor is really complicated, meaning you put a lot of weight on a lot of different classifiers, then the L1 norm will be huge. So if the L1 norm is huge, let's just take the L1 norm of w to infinity, then you're going to have a margin violation on every single data point. Okay, so if the L1 norm is large, then you have margin violations everywhere. So the way I would interpret the norm of w is as the complexity, like the real complexity of this predictor. So that's what we want for deep learning too. We want some measure of complexity that gets away from the number of nodes in the network, or the number of layers, or things like that. We want to depend on some other properties of the predictor. Okay, so as long as your normalized margin is good, then you will generalize. It doesn't matter all the other stuff. And let me just make another point, that going back to this paper that had bounds, or talked about random label and true labels, if you think about it, and we can prove this too, but if you think about it, the L1 norm of your predictor will be very large if you want to do well on random data. If you think, for random data, basically the data is completely unstructured, so you have to do a lot of work for each data point. So in some sense, the margin will kind of scale like n, the number of data points. And so this bound will actually become vacuous. It won't go to 0 with n. It'll actually increase. Okay. So like I was saying, everything so far in this story is consistent with what we were saying in this deep learning generalization story. But I'm not claiming that, it could be the case that in 5 years, margin theory actually doesn't explain like the most fine nitty-gritty parts of deep learning, and too bad. But so far it seems like it's explaining some stuff. Okay. So that's the generalization bound. So this is saying that so note that this thing has no algorithmic part. It doesn't say eta boost gives me a low test error predictor. It says if you give me a predictor that has good margins, then it generalizes. We still have to prove that the eta boost algorithm actually finds large margin predictors. Apologies self-cite for that one. So a couple years back, I proved that if we define gamma bar to be the maximum possible margin, and the maximum possible margin is cool because it's just some function of the data. Okay, so if this is the maximum possible margin, then after roughly 1 over gamma squared iterations, which is actually the same as the perceptron proof that I mentioned from Novikov 62, after roughly 1 over gamma squared iterations, eta boost finds a classifier that has some constant times the best possible margin. Okay? So that's pretty cool. Let me just go back to the previous slide. I realize I should have combined them for you separately. But so now what we can do is we can prove a stronger thing. We can combine the two theorems, and now we'll say the probability of error for the output of the algorithm is less than or equal to, and then we can just kill the first term because we get a perfect margin classifier, so that first term is just 0. And that second term, we replace gamma with gamma bar, the maximum margin, and we just put a 4 in the numerator. So we've just scaled it by constant. So this is proving that after 1 over gamma squared iterations, gamma bar squared iterations, the maximum possible margin, AdaBoost can output a predictor whose tester is at most, order 1 over gamma bar squared. Okay, so what we've done is we've proved both that the algorithm outputs a large margin predictor and that large margin predictor is generalized for boosting, not for deep nets. Yeah?
Are there any restrictions on the data?
Sorry, I didn't understand.
Are there any restrictions on the data?
The question is, are there any restrictions on the data? The answer is kind of no, and let me explain why it's completely intuitive and how the proof works. So boosting is a method that takes in this bag of classifiers, adds them up, and makes some output. So if you think about it, it's a linear classifier, it's a linear predictor over this new feature space defined by this bag of classifiers. So you don't actually care about the data because you don't even see the data. The algorithm only sees the outputs of the classifiers. So that's why it only depends on the VC dimension of H.
If I have the same X but different Y, data set have 2 Ys, the same X and different Y.
Oh yeah, so if you have same X with different Y, that means the data is not separable. So the best possible thing we can do here is the probability of margin violation. We're gonna have to give up on some points. So that first term there, probability of margin violation, if there are 2 such points, I'll fail on one of them. So I'll say that this term is 1 over n. Yeah, it's actually pretty cool. This, if you just stare closely at the theorem, I say given margin gamma, and then I allow some margin violations. So the duplicated point you mentioned would be a margin violation. Yeah, this is a really exciting theory. This kind of inspired many people, including me, and then biased me to use it for deep learning. Any other questions? We're doing okay on time, so. Okay. So yeah, a couple comments about this. So yeah, now you see my bias. I've been doing margins since 2013. And by the way, since many of you are young researchers, let me just say, I think it's healthy to, understand the biases of, all the papers you read and stuff like that. So this is my bias. I've been doing margins forever, so of course it was very natural for me to apply margins to deep learning. Let me just make a quick comment on the proof. I'll just say one intuition for the proof. AdaBoost uses the exponential loss, so that means sum over e to the minus unnormalized margins. So I take the log of that. The log of that looks just kind of like the max. So it actually already looks like the margin maximization problem. So if that sounded too vague, don't worry. The proof is actually quite short. That AdaBoost, which is not explicitly maximizing margins, is actually implicitly maximizing margins. Okay, and I think I've given most of this history. So above, I cited myself because this was the first and I guess only theorem that actually says something like after this many iterations based on gamma you get this margin. But there were a couple results before that were asymptotic. So in '98, this same paper that's proved this, they showed that asymptotically you get the maximum margin divided by 2. And asymptotically I mean in the number of iterations of the algorithm. So at some point it gets a good margin. And then it was shown a couple years later that by Tong Zhang and Bin Yu that if you change the step size a little bit, you can actually get margins that are maximal, but again asymptotically. Okay. Doing okay on time. So let me just say something that I'll use to describe margins for deep networks as well. There's a notion that people came up with back then called the margin plot. And let me explain this. So the margin was a quantity that was based on one data point. You give me an XY pair, and I output in the binary case fx times y. That's the unnormalized margin. So you can plot the margins for the entire training set, and then you get something people call a margin diagram or a margin distribution. And it kind of, if you interpret the margin as a confidence, it kind of says how your confidence varies over the training set. So people plotted these for AdaBoost and other boosting methods in a lot of their papers. And when I went upstairs and I checked this rethinking generalization paper that I started the talk with, I also started plotting margin diagrams. It was like the first thing I did. Okay, so let me just give you a little picture to kind of show you empirically that eta boost, what it does with the margins. So on the left here, I have the plot of the margin CDF. So what this is doing is I wrote down all the unnormalized margins, so f xi yi for all pairs xi yi, and then I just plotted a CDF. So at the right it has to go to 1 because all things eventually have, the largest margin is some positive number, and it starts at 0. And on the right, I have the contour plot. So I have some data that I synthetically generated, actually from a deep network, and I fit it with a boosting method. Okay, so everybody understands the two plots are. The left is maybe less familiar, this margin diagram. The right is the contour plot. So it's the contours of the real valued predictions themselves. So as we run training more and more, what we expect to happen is the margin diagram shifts to the right. All the margins should become positive. And we also expect the contour to delineate this red region. Okay, and indeed, that's what happens. As we run it, it goes to here. So 0 scrolled off of the left plot because we're getting a positive margin and everything. And indeed, we kind of mark out the red region with the 0 contour. Yeah, so the left one, sorry, I'm just doing recalibration in my head. So the left plot is for each pair of data point, for each data input, data output, XY pair, I can form an unnormalized margin, f of xi times yi. Okay, I have this unnormalized thing, unnormalized margin for every data point. Now what I can do, another way to interpret this plot is I take all those margins and I sort them. Okay, so I have all the margins of the data, of the training data. I want all of them to be very large, but for data, you actually kind of expect them all not to be the same. You expect maybe some of them to be large, some of them to be small. So another way to interpret this plot is every time there's a jump, that's one of the sort points for one of the margins. So this is the CDF of that set of sorted values. So the plot jumps by 1 over n every time I have a margin of that value in the training set. These plots are actually funny. They are not, they have a lot of information in them, and the people that worked on this just sort of came up with them and started putting them in all their papers, and it's not even clear who first came up with it. So yeah, they have a lot of information. Yeah?
So I understood that one iteration needs computing the weights of the last event classifier, but it seems that since the margins of the underlying classifiers are changing, this means you're updating also the underlying classifiers, right?
Sorry, say that again?
So what do you mean by an iteration in the boosting?
Oh, so the boosting algorithm, every iteration, it outputs another classifier.
So the underlying classifiers, what kind of weak classifiers are fixed?
No, they're potentially infinitely many. So it's not a fixed set. It's not a fixed finite set.
Yes, and so when each iteration updates which parameters?
So this particular boosting algorithm, it outputs one coefficient and adds one new classifier, but you can make other boosting algorithms that change more things. It doesn't actually matter. You can prove essentially the same theorem even if you change infinitely many per iteration. We can talk about this more offline, but I'm only saying offline, not because I don't know, but because we only have 5 minutes. But I should have repeated the question. So the question was, we're getting a different set of classifiers because add a boost adds another classifier every round, but if you change the boosting algorithm, all of it still goes through. Yeah, it's pretty cool. Okay, so here I've plotted a couple of these different contour plots for different methods. It's a little bit small, so maybe for those of you that did manage to download it, you can maybe look on your laptops. But the thing I want you to see in each of these plots is that all these so the top two, RBF SVM and quadratic SVM, these are explicit margin maximizing methods. Their training objective says, find me the max margin classifier. And indeed, for both of these, it doesn't just correctly label the data, it correctly labels the data, and the 0 contour is well separated between the closest the red and blue points. Okay, so if the top two find large margin classifiers, so does boosting. Boosting also finds a large margin classifier. But what's interesting, of course, is that the notion of large margin changes for each one of these. And so at this point, I want you to guess and soon I'm going to do a deep network on the same data. And I want you to guess what the margins look like, what the contours look like. Okay, so now I'm going to talk about generalization. And again, before lunch, I'll show you some plots that will give some evidence that empirically we get large margin deep networks. And after lunch, I'll give you the bound that corresponds to this. Okay, so as I kind of very strongly hinted, we can kind of guess what the ReLU network, but I really want everyone just to really think, just like commit to a guess of what they think it will be. I should say it was not what I expected at all. So again, I have two-dimensional data that I synthetically generated. All these methods are trained with the same data. The top two are explicit margin maximization. Boosting of stumps was not explicit margin maximization. ReLU network, I'm just doing cross-entropy training, no explicit margin maximization. So what is the contour plot going to look like? We know it's going to separate the data because I always get zero training error. So it looks like this, which to me is shockingly good. So the red region, it's hard to see, but there's a contour that's labeled with zeros. That's the zero contour. That means it labels plus on one side, minus on the other. And that zero contour really nicely is sitting far between the blue and the red parts, but it's not crazy and curved too much like the RBF SVM. But of course, I should say that for the RBF SVM, I could change the bandwidth and it would look somewhat better. So I shouldn't actually trash the kernel. But anyways, this is what the ReLU deep network does. I should say that I prepared this plot for a lecture of the undergrad course I taught, and I did not expect this answer, and I got it like 2 hours before class, and I was just like completely shocked and confused when I taught the lecture. I mean, for me, this is pretty shocking. This is a two-layer network with some ridiculous number of parameters, like more than a number of training points. So it has more parameters than training points. You could just memorize the training set and put little bumps around every data point for all it cares, but it did not do that. It could easily just put a bump around every training point. Everybody follow what I'm saying? There's nothing, it doesn't seem explicitly there's anything about this optimization problem that prevents it from just finding this like this tight shrink wrap of the blue side or the red side or something, but it doesn't do that. Okay, so I don't want you to get to lunch late, so we'll just do a little bit more of the punchline and then we'll start, I guess, with these plots. So if I do the same thing I did before, where I plot the unnormalized margin diagram for boosting, but now I also do it for these ReLU networks, and I just increase. Indeed, just like with the boosting, the zero scrolls off the CDF, which means I'm eventually getting all positive margins. Okay, so on synthetic data, I'm giving you evidence that we are doing margin maximization. And the three-layer ReLU contour and the two-layer ReLU contour don't change that much. Also interesting. And I'll just maybe end with a little bit of a puzzle that I think is a cute puzzle. And of course, you can download the punchline, but whatever, maybe don't for a second. So here's a little bit of a puzzle. So here's a slightly different margin diagram. I'm plotting the margin PDF. So not the CDF of the margins, but the PDF. It was just easier to visualize. So earlier I had synthetic data, now I have CFAR. So for CFAR, if I train up this deep network, standard AlexNet deep network, and I plot the margins, they look like this. So 0 is on the left of the distribution, which means I have positive margins on everything, but I haven't told you the normalization. Remember that for margins I was telling you the normalization is essential. I've left off the normalization here. If I look at CFAR with true labels and CFAR with random labels, and I don't play with the normalization, the margins look the same. So in other words, the margins seem to have an issue that random and true labels get the same margins. So it seems like margin theory so far is broken because it's giving the same confidence, if you interpret margin as confidence, on random and true data, which doesn't make any sense. It should have better confidence on the true data. So we'll start with this puzzle when we come back. The question was, is a margin a measure of uncertainty? The answer is, you can intuit it as a measure of uncertainty, but then if we actually try to make this rigorous, like there's something called calibration, which is if a prediction's calibrated and it says 0.9, that means 9 out of 10 times like it's supposed to happen, it happens. I'm not making any claims about it being like that, so I'm calling it intuitively a notion of confidence, but it's not really explicitly a notion of confidence. Okay, so let's go back to where we were. So just to remind everybody, we're talking about generalization and optimization today, and I told you because of my own expertise or lack of expertise, I'm giving you a margin perspective on it. And so far what we did was we talked about margins in boosting, where there's a very compelling story. You can empirically verify that eta boost is, and these boosting methods are finding large margin predictors. You can prove that they find large margin predictors, and then you can prove that large margin predictors generalize. And so now our goal is to repeat this entire story for deep networks. We want to say that deep networks empirically find, or gradient descent on deep networks empirically finds large margin predictors. We want to prove they generalize, and then we want to prove that gradient descent did what we observed that it did. And where we left the story off was on this set of plots. So this is actually a little bit more refined than what I was saying. Let's look at the right-hand plot here. So there are two curves, and I apologize to many people after in the questions. I did not very carefully describe these margin CDFs. Let me just say how to, kind of the first order way to interpret this plot. So the right-hand plot, the key thing going on here is the green curve is for CFAR with random labels, and there's a big mass of margins, so most of the margins of the predictions are near zero, whereas for CFAR with the true labels, they're far to the right. They're farther from zero than for random labels. So the way to interpret this is that if we use a normalization that I'll give you in a couple slides, if we use a specific normalization for the margins, then it looks like we get better margins on CFAR with true labels than on random labels. Why does that matter to us? In the end, we're going to prove a generalization bound that says your generalization scales with normalized margins, and therefore the bound will say that your generalization is better on true labels than on random labels. So the reason this plot is valuable to show you is that that paper I started this discussion with, the paper, the Rethinking Generalization paper, one of the claims in it is that a lot of statistical learning theory has trouble telling the difference between random and true labels. They get the same bound either way. But now if we make a generalization bound based on normalized labels, the bound will be different. It'll be better for true labels than for random labels. Okay, so that's the meaning of this plot. Okay, let's keep going. So I haven't made it completely explicit, but indeed, if you plot the normalized margins, and again, I haven't told you what this normalization constant is, but if you plot the normalized margins and you run gradient descent over time, so that's what this plot is. It's the PDF now of the margin diagram of the margins. So you plot this over time, gradient descent on deep networks with cross entropy loss is indeed finding better and better margin predictors. So why is this interesting? Somebody asked me during the break, what was the regularization used? The regularization was 0. I did not regularize. This is gradient descent with no, or SGD with no regularization, just on cross entropy. And indeed it is finding it is increasing the normalized margins of the predictors. Super interesting. So this is what I was promising at the beginning of the talk, or hinting would happen. So indeed it appears that that gradient descent on standard deep networks, this is AlexNet. This is AlexNet on CFAR, is finding large margin predictors. Okay, empirical so far, no math yet, but this is just empirical verification. Okay, so what we have so far, I think I just said all of this, is gradient descent seems to select large margin deep networks, and the margins are worse on random labels, which was also the case with boosting, so we hope that the bound will actually be kind of nicely data dependent. It'll reflect kind of good structure in the data or not. Okay, so now we have to produce an actual generalization bound. So the bound will be a mirror of the one we produced for the boosting. It'll say if you hand me a predictor with a good margin, then it will have a good generalization bound. So to be clear, I'm not saying the bound is giving us a guarantee on gradient descent. That's the theorem we want. We want a theorem that says if you run gradient descent on a standard architecture with good data, you get low test error. That's not the bound I'm giving you. I'm just giving you a bound that says if you give me something that has a good margin, then you have a good test error. And that filling in the gap and getting a gradient descent guarantee is super difficult because that's non-convex, et cetera, et cetera. Okay, actually, let me check the time to make sure we cover enough of the slides. Okay, so let me give you the bound. So here's a bound that a group of us worked very hard to produce 2 years ago. So the bound has some similarity to the eta boost bound, but then with a couple interesting differences. So it says, hand me an architecture, so hand me some fixed, ReLU or whatever architecture, so what's still variable are the weights. I require the activations to be row Lipschitz. The reason this is cool is because this bound works for things like max pooling and convlares and all. It handles all sorts of stuff. It doesn't just need univariate gates or something. Okay, so with probability 1 minus delta over the data, just like last time, give me a margin and give me some set of weights, and now I have this bound. So the top line is actually the same as we had before. The top line says probability of misclassification is less equal to probability of misclassification on the training set, or sorry, misclassification with margin gamma, so margin violation, plus this whatever nuisance term, log 1 over delta over n, square root. And now we have the margin term. So before, the margin term for the previous bound looked like 1 over gamma times square root VC over n. Now we're going to have, we hope, 1 over gamma times a bunch of stuff that captures the complexity of the network. So all the stuff that isn't margin is actually the normalization. So I've been saying, what is normalization constant? This gives one choice of normalization constant. Okay, so let's go through these terms one by one. So again, this is just like the eta boost bound. The only difference is the things in color. Okay, so the first term is the data term. Let me explain this term. So X is all the data written as a matrix. So it's an n by d matrix, n rows for n data points, d columns. So if you just want to sort of coarsely upper bound this thing looks like root n times some bound on the individual elements. So you can also interpret this blue term as just being constant over root n. So it's kind of like the constant over root n we had before. Okay, so now before we normalized the margin by the L1 norm. So now it's natural to wonder, what do we normalize the margin by for the deep network? Is it the L2 norm of the weights? Is it the L1 norm of the weights? It's going to be something quite a bit different. So the first term of the normalization, and then there's this nuisance term. The first term of normalization is the product of the spectral norms of the weight matrices times the Lipschitz constants of these activations. Lipschitz constant of ReLU is 1. Lipschitz constant of max pooling is small, so I'm just going to drop that term. So it's product of these spectral norms. You can interpret that as a upper bound on the Lipschitz constant network. So if we had a linear function, then it would just be actually the product of these spectral norms. Okay. So far this is somewhat, at least readable, somewhat legible. This nuisance term is going to look pretty strange if you haven't seen it before, and I'll explain it kind of carefully. So this nuisance term, what it does is it looks at every layer, summation over the layers, and it looks at, there are a couple ways to write this bound down. In this version, it looks at the distance from initialization to one norm. So what that means is I look over all the nodes in a layer, I take I take the L2 norm of those weights from initialization and sum them up for that layer. And the denominator I scale by the spectral norm of that layer. So a few sanity checks on that term. One thing we can say about it is that it's, a priori, we can't make a bound for this term that isn't better than just the number of layers. So this term can be pretty bad. Okay, but this is the bound, and again, to compare it to what we had for boosting we had the L1 norm on the numerator and the margin on the denominator. So when I've been plotting all of these margin CDFs, I've been normalizing by all of this stuff. Just invert this whole right-hand side. Okay, so this is a bound. Let me make a few comments on it. So like I said, it's never been a Lipschitz constant. The bound is, you could argue, predictive of empirical performance. I'm not claiming any causal relationship between these terms and what's in the bounds, but it's predictive in the sense that if I normalize in the way I said, then random labels and true labels were separated and a bunch of others. And yeah, I'll skip the rest of those comments. So here was the plot I showed you earlier where if I do this normalization, the random labels get worse margins than the true labels. You can do a bunch of other normalization, other plots for other kinds of data. One that's kind of cute is that MNIST has larger margins than CFAR, which is also something you would expect, yada yada. So this is why it seems somewhat predictive. So I should say this bound is not remotely tight. This bound is very loose. If you compute it on something like CFAR, it's massive. It's larger than 1. And 1 is a trivial upper bound on the probability. So it's a bad bound in that sense, but it's good in the sense that it's somewhat predictive. So if you're looking at this and wondering what is the next thing that you could do or what could you work on if this is interesting, well, the right-hand side is super loose. There's no sense in which any of these terms are necessary on the right-hand side. Everything here could be improved drastically. Okay. One other comment I'll give briefly, because people want me to talk about optimization a lot. So one other brief comment I'll give is that an interesting thing about this is to compare it to lower bounds. So I'll make 2 comments here. So to compare this to lower bounds, everything I've written here, so turn the nuisance into 1, then that is the lower bound that people have. The best lower bound people have for the right-hand side is just the current right-hand side with the nuisance equal to 1, which is pretty bad considering the nuisance term is actually that weird thing. And what the lower bound is the lower bound for linear functions. So let me make a connection to yesterday's talk. So yesterday's talk was talking about approximation power, and another way to interpret yesterday's talk was it was kind of telling us what deep networks can look like, what functions they can approximate and stuff like that. The lower bound here is saying that the best lower bounds, the best kind of complicated function we can construct and on the right-hand side is just a linear function. So I would actually claim that this is a sort of approximation theory weakness on the right-hand side. So if people are curious, you can try to improve this lower bound. I think that's all I'll say about it for now. Yeah, I think if you're curious about other work and things like that, you can look at the slides or ask me later. Otherwise, I'll stop with any questions on this. Yeah? Sorry? Yeah, so this is a very important question to clarify. So the question is this for gradient descent or stochastic gradient descent? There's nothing algorithmic in this theorem. This theorem says if you hand me a classifier and it satisfies certain conditions, in this case margin blah, 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 then it has this generalization bound. But it doesn't say anything about the output of gradient descent or stochastic gradient descent. That is what we would dream to prove, and that's what we still have about 30 minutes to talk about. Yeah, the dream theorem says, gradient descent gets this bound. That's the dream theorem, which we got for boosting, but we don't have for this. Any other questions? So yeah, again, I have no claim, so bias release, I have no claim that this right-hand side is tight. It is super bad and super loose. It's larger than 1. Also, maybe if an infinite number of IQ points were spent trying to reduce the right-hand side, it's still doomed. It's possible that this will never be able to explain generalization deep networks. Maybe that's the case. Who knows? But this is where we are now. So just for comparison, I want to give another bound. So I want to give a VC dimension bound. So this bound, it's cited 2017, but actually the flavor of the proof is actually decades old, and just a small modification. So this is a very interesting bound to compare against the previous ones. This one says the VC dimension, and if you don't know what VC dimension is, don't worry, I'll give you the key point. Maybe I'll do it now. Okay. So the VC dimension is essentially exactly the number of parameters from the number of layers. And if you don't know what VC dimension is, all you need to know for this slide is that VC dimension tells us that a test error is less than or equal to the train error plus square root parameters times layers over n. So yeah, there are, one interesting thing about, if we go back all the way to like the 10th minute of yesterday's, well, I think the 10th minute might have been a Skype call, but we go like the 10th minute of some part of yesterday's talk. I was mentioning that one cool thing about deep learning is it makes us rethink many things about machine learning that have no relevance to deep learning. So VC dimension seems to have some inherent looseness which causes it not to be relevant here. Specifically, this VC dimension bound is tight. So the VC dimension, you can compute it and it's really P times L. It's not upper bounded by P times L, it's P times L. On the other hand, in most standard deep networks, number of parameters is larger than the number of data points. So the bound is bigger than 1 just from the outset, but it's a tight bound. So I personally actually like this bound a lot because if you go through the proof, it reveals a lot of interesting structure of deep networks, which is actually not captured in this proof. This proof is kind of coarser in some senses. And maybe somebody could figure out a better, like a small modification of VC dimension that makes it more data dependent or something, and then they could go back and apply it to non-deep learning. So there are non-deep learning consequences of weird deep learning questions. And just to give a comparison, if you change the activation function, it's actually very interesting what happens. So the only case that's tight that people know is ReLU, that's P times L. If you use threshold gates, it's P. If you use polynomial, it's PL squared, but that's only an upper bound, sigmoid. And if you really pick a weird activation, you can accidentally get infinity. So there's all this weird variation here. It's hard to guess the bounds, and it's very hard to prove these bounds too. These proofs are actually harder. The sigmoid proof is, I'd say, like 100 orders of magnitude harder than this proof. Any questions? So the way to interpret this is that this bound looks loose because it's large number of parameters. This bound was attacked in that kind of a very strong hint about what should be happening. So this is a linear predictor. So it's a rank 1 matrix. So if W4 times W3, W2, W1, it would not make any sense for these all to be full rank matrices. They're full rank at initialization, the probability 1, but it'd be kind of wasting effort if the norms of all, if the ranks of all these matrices were large, because in the end they product together and become a rank 1 matrix. So indeed that's what happens. If you plot essentially the ranks of the matrices over time, the Frobenius to spectral norm ratios, they converge to 1. So all these weight matrices have become asymptotically rank 1. Okay? So I'll skip this plot, but in the end, this is what you can prove, which is, so it's not only the case that you get 0 training error, but you get not only a large margin predictor, so W1 times WL minus 1 yada yada, W1 is a large margin predictor. It's also the case that you're individually finding a minimal solution with respect to all the individual weight matrices. So I'm kind of wasting no norm. This thing, what I've written here implies many things. It's a little bit hard to unpack the linear algebra, but I'll just make a number of comments. So this theorem, it implies that the matrices become asymptotically rank 1. It implies something even stronger, which is that if I write, so they're asymptotically rank 1. So WL is UL VL transpose, single rank 1 thing. UL minus, or VL, WL minus 1 is UL minus 1 VL minus 1 transpose, that's the SVD. It turns out that VL minus 1 becomes UL minus 1, VL minus 2 becomes UL minus 3, and yada yada. So all the singular matrices, singular values align. So the matrices become mutually aligned. So for me, this is one of the shocks of deep learning. I run gradient descent on a non-convex objective, and it doesn't just get training error 0. It gets this ridiculous well-conditioned solution. It gets this ridiculous well-conditioned solution with aligned weight matrices and small spectral norm and small stable ranks and all this stuff. So even if it's not a ReLU theorem, it's pretty mind-blowing in terms of the fact that this happens. It's pretty shocking. Okay, so there's one, I'm actually going to skip the discussion because I want, like I promised, I'd spend a majority of the time on some other people's work. Is there any question about this? I went a little bit too fast because I wanted to get to the other thing. Let me just summarize. So we're trying to prove that we get large margin predictors as the output of gradient descent, because that will plug into our generalization story. And all I'm able to prove for you so far is the linear case and the multilinear case, where it's a product of weight matrices. I'm actually going to shift gears now and not talk about margins for a moment. So for those of you that have been following this literature, there's a tremendous number of papers that are claiming you can get very small training error if you just run gradient descent on standard architectures with large width, with overparameterization. Just a curiosity, I've shown of hands, how many people have seen these papers? Okay, yeah, this is a very prominent field of research with lots of very cool techniques going on. And so let me just make a few comments on it. So let me explain it slowly because there are some very nice conceptual things in this work. And yeah, finally, bias warning, I am not involved in any of this work. Okay, so just to fix some notation, so now I'm writing down the prediction of the network on an input x is fx semicolon w. So w are my parameters. I'm making my parameters explicit now. Sometimes before I was dropping the w. Okay, fx semicolon w. So just for convenience, the loss on data point I, I'm writing it just as L subscript I. You can just interpret this as cross entropy or whatever. Okay. So by the chain rule, this is the gradient descent step. Same thing that Justin gave yesterday or whatever. So it's, by the chain rule, this is the gradient descent step. The gradient passes through the average, and then I have the derivative of the loss, and then I have the gradient of the parameters. Okay, nothing interesting so far. The really kind of cool thing to think about is, so this equation, this update is telling us how the parameters evolve, but how do the predictions evolve, right? Natural question. How did the prediction on x evolve as a result of gradient descent? So the answer is complicated, but why don't we just use a Taylor expansion? Okay, so to be clear, I mean, it's on the next bullet point, but I just want everybody to know what we're about to look at. So right now I'm giving the definition of gradient descent just via chain rule, and it's in terms of the parameters. Now I want to know what gradient descent does to the predictions. So what it does to fx semicolon w. That's hard to write down, so I'll write it down as a Taylor expansion. So I've written down the Taylor expansion. So if I look at fx w prime being after gradient descent, so the first step, I'm just writing down a Taylor expansion. So to be clear, there are quadratic terms. I'm dropping the rest of the Taylor expansion, just first order Taylor expansion. So that's why it says approx. And if I just fill in, so that's the prox sign, and to get to the next line, I'm just filling in w prime minus w with a definition of gradient descent. Okay, that's all I've done, plugged in definition of gradient descent. Now this is becoming very interesting because I have grad w f transpose grad w f, and the only thing that changes in that red term from one side to the other is x and xi. So does this remind anybody of anything else we've seen today in somebody else's lecture? So treat w as a constant. What does this look like? It looks like a kernel. I mean, I guess that's some of the hints away because it's like on the slide, but you can interpret this as a kernel. So in particular, if w in the right-hand side is fixed, so if I just take this update rule and I fix w in that term, then this is the evolution of a linear function with that kernel, of a linear predictor over that kernel space. Okay, so if eta becomes very small, then this is kind of legit, and these dynamics are dominated by this kernel function. Okay, so far this is just like a formalism. It's just like kind of interesting. It's not shocking yet. What becomes shocking is when you start playing with it. So I want to make sure that all of this material is clear. And so I might only kind of vaguely give the connection to margins. So don't worry if we run out of time talking about this. I'm actually happy with that because there's a lot of neat stuff in these papers. And I'll give the full reference list in a second. A lot of people work on this. More people are working on this than on margins. Okay. So as I was saying, if we just make this a constant, so I'm replacing grad w of this kernel, I'm doing two modifications. Instead of having the kernel being defined by this w, the current w, I'm replacing with the initial w, and I'm throwing in the expectation. So it will be the case that this thing is a mathematically nice object, but what's more interesting is, does this relate to deep learning? So again, I have the deep learning model, which if the step size is small, evolves according to that first kernel. That first kernel dictates how the model evolves. The second kernel is just some math construct we made via Taylor expansion and stuff. There's no reason to believe a priori that this has any relationship to deep networks. Okay, I fixed the weights, I added an expectation, like why is this related to deep networks? Okay, so just a quick sanity check to reason about this more. If I'm in a linear model, so no activations, just one layer, then grad wfx is just x. So this kernel becomes a linear kernel. We're back in linear land. Everything makes sense. This is just like a quick sanity check that if you go through the papers related to this, you can check. Okay, another way to look at this is that if we work with that first model, the second model, so if we replace that kernel with this expectation first weight matrix, initialization weight matrix kernel, then it's a convex problem with a linear weights over this kernel representation. So this is something we can completely understand. So again, I have two models now. I have the original deep network whose dynamics are governed by this time-varying kernel. And then I have this second thing where I've fixed the initial kernel and taken its expectation, and that governs my dynamics. So I have two different predictors that I'm looking at. And the second one is what people call the NTK, the neural tangent kernel. It's called tangent because it's tangent at the initialization. It's called neural because of neural net, I guess. It's called kernel because Arthur's in the room. Just kidding. But, okay, so I have to say that what's shocking to me mathematically is how nicely the math goes through if you try to analyze what this object is. So you can actually explicitly write down this kernel for, well, let me just give two facts. So you can explicitly write down the kernel for ReLU networks, and you can use the techniques in this 2009 paper way predating this NTK literature to find it. I can also say for the deep linear case, okay, the deep linear case, I was like, oh, it's so magical that this works at all. For the deep linear case, you can work out the kernel. Does anyone want to guess what the kernel is for the deep linear case? Oh, let me say another quick fact. Another nice thing about these kernels is they actually decouple over layers. So the kernel for an L-layer network is the sum of the individual kernels per layer. So does anyone want to guess what the kernel is for a deep linear network that has all identity activations? Just don't even think, just make a guess. What's like the gut feeling guess? Deep linear kernel. So deep linear kernel, it's learning a linear predictor in the end. If you just work out you just exactly work out with equalities the expectations, that kernel is a linear kernel with rescaling, just verbatim. And it's actually very quick to prove. You just use properties of the trace and it just gives you the linear kernel. Okay, so, okay, I've told you it's a cool mathematical object, and I'm getting kind of excited because it's very, very cool. Now the question is, what is the relevance to deep networks? I have the NTK, which is not a deep network. It's this weird linearized RKHS thing, and then I have the deep network. What is the relationship? So the interesting thing is that the relationship is extremely subtle and not fully understood. There are many different camps. People believe different things. I'm always surprised by what people tell me about it. I was visiting one of the Google offices, and I actually just made this very strong claim that the NTK is different from the deep network in this specific regime. And the guy was just like, what? And he pulled out his laptop and showed me stacks of plots that were actually exactly contradicting what I just said. So the relationship between these two models is very delicate and very interesting. You can write lots of papers with very different details. I'll just give some highlights. Mathematically, one thing you can prove is that as the width of the network goes to infinity and the step size goes to 0, then you can prove two things. One, that the weights on the individual nodes, so the rows of those weight matrices, those change less and less. And you can also prove that a deep network becomes equivalent to the NTK. Yeah, it's very, very fascinating. There's a very pretty proof in this Chizat and Bach paper. This is not the first analysis of this type, but it's a very pretty proof. I should say this pretty proof does kind of assume away a lot of the complexity. It assumes that the smoothness constant, blah, 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 blah. You have to prove all those things, but it's a very pretty proof. Then if you're familiar with many of the related works, so NTK was by, I don't know how to pronounce this. Can somebody say it for me? The first one's a French name, I believe. Can somebody help me? Okay, their names are there. And so then there's a lot of optimization papers by Alan Zhu, Simon Du, Jason Liu, and Jolie, and lots of people. And even though the papers do not say NTK because some of them predate NTK, if you look at the proofs, you will see Taylor expansions around initialization, expectations of this, blah, blah, blah. So these papers, most of these papers are in that regime. And I can give a quick intuition for why this is the case. And this intuition is in the, it's in the Chizat-Bach paper. There are other intuitions. I'm just copy pasting to you their intuition. Here's the intuition. So if you just go to Google PyTorch documentation, the PyTorch documentation tells you that the initialization is based on the fan-in. Okay, your initialization goes down with the width of the previous layer. So if I'm increasing the width of my network, then I'm going closer and closer to 0, basically. So the way the Chizat and Bach paper explains it, again, there are other explanations, but what it's saying is that you're zooming in onto the risk surface and it's becoming locally more and more flat as you zoom in. That's one explanation of what's going on. I should also say that some of these same authors, but also many other authors like Andrea Montanari and people he works with, they have a very, at the beginning, first glance, similar looking set of papers using something called a mean field analysis. If you're just curious what the relationship is, they actually do differ. They prove a different theorem with some of the same lemmas, but also some different lemmas with fundamentally different things going on under the hood. Okay, was there a clearing throat for a question, or okay? So where are we with this? So I'll just, because I want to make sure that we're all at least settled on these, and then I should conclude, and maybe I'll stop a minute after. We have 30 minutes break, right? So 1 minute isn't like too lethal, right? 30 minutes? Two minutes left. The key things I want you to take away from this is that this is what I know. So it is true that so if you take the step size small and you stay in the first couple iterations of the gradient descent, the NTK and I'm talking about empirically, the NTK and the deep network do stay close. There are certain cases where they stay close longer, but it's not really well understood. But you can find many papers empirically how close they are, when they're close, what makes it different. I've been told that confidence make them differ more. Another thing that's key to point out here is that these results only give 0 training error. They do not say anything about test error. If you apply a standard generalization bound to the output of the NTK analysis, then it blows up. It blows up in a lot of ways. So this does not imply zero test error. And this is the main reason I was studying the margin thing, because I wanted to prove 0 test error. But that's the main thing I want to say about this. Let me just summarize and then conclude. So in this talk, I gave a few things. So one was that I said that we started with this rethinking generalization paper and pointed out that not only are optimization and generalization wide open for deep networks, they're also very confusing. There are magical things like 0 training error on a non-convex problem with random labels. The next, so that was our starting point. Then I proposed margin theory, which worked for eta boost, and we analyzed it for eta boost and showed that not only do we get bounds for the generalization, but also bounds that the algorithm outputs a large margin predictor. And then I talked a little bit about what happens for deep networks, both optimization and generalization. And for people here that are interested in this literature, in the optimization community, the main body of work right now is not the margin approach, it is this NTK approach. And I gave some of the references here. You're free to ask me about many of the other references. But so I'll stop there.